Welcome back to the Deep Dive. Today, we're going to be taking a deep dive into a paper that really caught my eye.
Oh, yeah.
Yeah, it tackles a challenge that I know you face every day working in computational finance,
Okay.
and that's how diffusion models can handle really complex high-dimensional data.
Yeah, you're right. That is a key issue. And
Yeah.
this paper uses some really clever physics analogies to break down what happens as these models
Cool.
try to learn from these massive data sets. And more importantly,
Right.
when they go wrong
Yeah.
and just start memorizing instead of generalizing.
Okay, so they're looking specifically at the backward diffusion part of the process,
Exactly.
where the model is trying to reconstruct data by removing noise.
That's it.
Okay.
And they've identified 3 distinct phases or regimes
Okay.
the model goes through during this backward diffusion process. And get this.
Okay.
Each regime is marked by a specific behavior that tells us a lot about how well the model is actually learning.
I'm all ears. Let's start with regime 1.
Yeah.
What's happening there?
Regime 1, it's basically chaos.
Okay.
The model is generating pure noise. So think of it like trying to build a picture of the market from static on a TV screen.
Okay.
It's not picking up on any meaningful patterns yet.
Got it.
Yeah.
So how do we get from that static to something that actually resembles,
Right.
A realistic order book or something like that?
Well, that's where regime 2 comes in.
Okay.
This is where things start to get interesting.
Okay.
The model begins to identify distinct classes of data,
Interesting.
like differentiating between a bull market and a bear market in price movements.
Yeah.
Or maybe even spotting those telltale signs of high-frequency trading in an order book.
Okay, so it's starting to see the forest
Yeah.
for the trees, so to speak, picking out those broad patterns that define different market states.
You got it. And the paper calls this transition from random noise to recognizing these species of data.
Okay.
They call it the speciation time.
Speciation time. Okay.
Yeah.
I'm guessing there's a way to actually calculate this and not just eyeball it.
Yeah, you bet.
That's right.
The paper gets a bit technical here, but essentially they found that speciation time
Okay.
can be pinpointed
Yeah.
using the eigenvalue of the principal component of the data's covariance matrix.
Okay.
Don't worry too much about the math for now. What it means in practice is identifying that strongest force
Okay.
shaping your data.
Got it.
It's like finding the market's heartbeat.
That's a great way to put it.
Yeah.
So we've got regime 1, pure noise, regime 2, where it's starting to make sense of things.
Yes.
But there's a third regime, right?
Right.
Where does that fit in?
Regime 3 is where we see the downside of the model getting too smart. So instead of continuing to generalize, it starts to fixate on specific data points from its training set.
Okay.
It begins to memorize.
Oh, that doesn't sound good.
Not good.
So it's like the model's going from
Right.
understanding the overall market dynamics to just spitting back out historical data points.
Yes.
Which is not helpful if we're trying to use it to
Not helpful.
simulate potential future market scenarios or anything like that.
You hit the nail on the head.
Yeah.
The paper calls this point
Okay.
the collapse time.
Okay.
It's when the model transitions from generalization to memorization, which, as you said, is not ideal.
Yeah.
And they link this collapse to something called excess entropy.
Excess entropy.
Essentially a measure of how much surprise is left in the generated data.
So the less surprised, the closer the model is to just parroting back the training data.
Exactly.
Okay.
And for someone like you working with financial data, this means being really careful about the balance between your model's complexity and the size of your data set.
Okay.
Too much data, and you risk pushing your diffusion model right into regime 3 memorization city.
Memorization city. I'm getting flashbacks to cramming for exams in college.
Right.
Where I'm just memorizing facts, but not really understanding the material.
Great analogy.
Yeah.
And this brings us to a big challenge
that
the paper emphasizes. The curse of dimensionality.
Curse of dimensionality. That sounds ominous.
Well, that can feel like a monster sometimes.
Okay.
It basically means that as the number of variables in your data explodes, the amount of data you need to avoid that collapse into memorization grows exponentially.
Okay.
And financial data, as you know.
It has a ton of variables.
A ton of variables.
Yeah. Imagine trying to model the entire global economy.
Right.
You would be drowning in data.
Drowning in data.
Let alone making sense of it.
Exactly.
Yeah.
The curse of dimensionality highlights why even the most sophisticated models need to be incredibly focused. You can't include every single variable under the sun without risking that dreaded collapse into memorization.
Okay, so we've got these three regimes.
Yeah.
Speciation, where the models figure out the broad strokes collapse, where it gets lost in the weeds. And that sweet spot in between where the real magic happens.
Yes.
This is starting to make a lot of sense, but I am eager to hear how all of this actually translates into practical advice.
You're in luck.
Okay.
This paper is full of useful takeaways.
Okay, great.
And in our next segment, we'll dive into some of the key strategies they suggest for navigating these regimes effectively.
I can't wait.
Okay. So, to pick up where we left off the paper, doesn't just point out these three regimes.
Right.
It also gives us tools to actually deal with them.
Okay, that's what I was hoping for.
Yeah.
Theory is great, but I'm all about that practical stuff. So how do I actually use this knowledge when I'm building and training my models?
Well, the first step is awareness.
Okay.
Just knowing that these regimes exist and being able to spot the signs of each one as your model trains is huge. It's like understanding the different phases of a market cycle.
Right.
If you know where you are, you can make much smarter decisions.
That makes sense. So if I'm seeing my model start to get a little too good at replicating the training data, that's a red flag that I might be heading towards collapse time. Right.
Exactly. And that's when you need to bring in the big guns.
Okay.
Regularization techniques.
Ah, yes. Regularization.
Yes.
I remember from my machine learning days, it's all about adding constraints to the model to prevent overfitting.
Yeah.
But there are a lot of different techniques out there.
Right.
Any guidance from the paper on which ones are particularly useful for someone working with like financial time series data?
Yeah, they do touch on that. And it's a crucial point. You're absolutely right.
Yeah.
Not all regularization techniques are created equal.
Right.
The key is to choose techniques that align with the specific characteristics of your data and the goal of your model.
So for something like modeling order book dynamics, where the relationships between variables can be incredibly complex and nonlinear, what kind of regularization techniques would be most effective?
That's where things get really interesting.
Okay.
You might want to consider techniques like L1 or L2 regularization, which essentially penalize the model for having too many complex features.
So it's like telling the model to keep things simple.
Exactly.
And focus on the most important relationships.
That's a great way to put it.
Like pruning a tree.
Yeah.
Getting rid of those extraneous branches to allow the core structure to grow stronger.
Yeah. And for time series data specifically, there are techniques like dropout, where you randomly turn off certain connections in the neural network during training.
Interesting.
And this forces the model to learn more robust and generalizable patterns.
So it's like making sure the model isn't leaning too heavily on
on
any one piece of information.
Yeah.
Preventing it from like becoming over-reliant on any single crutch, so to speak. Got it.
Yes.
This is all super helpful.
Good.
But going back to those regimes for a moment, I'm curious about that transition from noise to something meaningful, the speciation time.
Right.
What does that actually look like in practice?
Yeah.
If I'm training a DM on order book data, for example, what kind of species might I expect to see emerge during this phase?
Great question.
Yeah.
It would likely reflect the distinct types of market behaviors that shape the order book. You might see species emerge that represent periods of high volatility versus low volatility.
Interesting.
Or maybe patterns associated with different types of traders. Algorithmic traders versus human traders.
That's fascinating. So the model is essentially learning to speak the language of the market.
Yeah.
Recognizing those different dialects of order book behavior.
And the cool thing is, by understanding these regimes and using these regularization techniques, you can actually guide that learning process.
This is making me think about something we touched on earlier. The curse of dimensionality.
Right.
Financial data is inherently high dimensional.
It is.
So how do we even begin to tackle that beast when building our diffusion models?
Yeah.
Are we doomed from the start?
Not at all.
Okay.
The curse of dimensionality is a challenge, but it's not insurmountable. Remember those two key strategies we mentioned?
You mean being smart about which data to include and using regularization effectively?
Precisely.
Okay.
First, you need to be ruthlessly selective about the variables you include in your model.
Okay.
You can't just throw the entire financial universe at it and expect good results.
Right.
You need to think carefully about which variables are most relevant to the specific problem you're trying to solve.
So for someone building a model to generate realistic order book data, what kind of variables would you prioritize?
Well, obviously, you'd want to include things like bid and ask prices, volume and order arrival rates.
Okay.
But you might also want to consider factors like market depth, volatility, and even sentiment data derived from news headlines or social media.
It's about striking a balance between capturing enough of the market's complexity without overloading the model.
Exactly. And that's where regularization comes in.
Right.
By adding the right constraints, you can help the model focus on the most important relationships in the data, even in high-dimensional spaces.
So regularization is like our secret weapon in the fight against the curse of dimensionality.
It's definitely one of our most powerful tools. But remember, it's not a magic bullet.
Right.
It's about using these techniques thoughtfully and strategically in conjunction with careful feature selection and domain expertise.
This is all starting to make a lot of sense.
Good.
But you know me, I always like to push things a bit further. Let's say we've mastered these techniques. And we're building diffusion models that can generate incredibly realistic, synthetic financial data.
Right.
What are some of the exciting applications of this technology, particularly in the world of computational finance?
That's where the real fun begins. I think we're just scratching the surface of what's possible with these models.
Yeah.
But here are a few areas where I see huge potential.
Hit me with it.
First, think about risk management. Imagine being able to stress test your portfolio against a vast universe of synthetic market scenarios, including those rare black swan events that are so difficult to model using traditional methods that could revolutionize the way we assess and mitigate risk.
That would be game-changing. Instead of relying on historical data, which may not capture the full spectrum of potential risks, we could use synthetic data to explore a much wider range of possibilities.
And it's not just about risk management. Think about algorithmic trading. These models could be used to train and test new trading strategies in incredibly realistic simulated environments.
Interesting.
This could help us identify profitable strategies more quickly and with less risk.
So it's like having a market simulator on steroids.
Exactly.
You could run thousands of experiments without risking a dime of real money.
Precisely. And this could also lead to the development of more robust and adaptable trading algorithms that can better handle unexpected market conditions.
This is all incredibly exciting. But let's not forget about the potential ethical considerations. If these models become really good at generating synthetic data that's indistinguishable from real market data, couldn't that be misused?
You raise a really important point. As with any powerful technology, there's always the potential for misuse. It's crucial that we develop ethical guidelines and safeguards to ensure that these models are used responsibly.
Absolutely. It's like giving someone a powerful new tool. We need to make sure they use it for good, not for harm.
Well said. And this is why conversations like this are so important. The more we understand about these models, their capabilities and their limitations, the better equipped we'll be to harness their power for positive impact.
I couldn't agree more. But before we get too lost in the ethical implications, let's bring it back to the technical side of things. The paper mentioned a fascinating connection between the behavior of diffusion models and something called the random energy model from physics. Can you shed some light on that?
Yes. This is where things get a bit mind-bending. The random energy model is a concept used in physics to study complex systems with a lot of randomness. Like, well, financial markets.
So how does a model from physics relate to a machine learning technique used to analyze financial data?
Yeah, that's a great question. It is, and it's one of the things that makes this paper so groundbreaking. Essentially, they found that the process of a diffusion model collapsing into memorization can be understood through the lens of this random energy model.
I need a bit more hand-holding here. Can you break this down for me?
Imagine each data point in your training set
Okay.
as a tiny energy, like a small valley in a mountainous landscape.
Got it. I can picture that.
Now, during the backward diffusion process, think of the model as a ball rolling around on this landscape.
Okay.
At the beginning, when there's a lot of noise, the ball has enough energy to bounce around freely, exploring different valleys.
It's generalizing.
It's generalizing.
High energy, lots of movement.
Exactly. Right. But as the noise decreases, the ball loses energy and starts to settle into one of those valleys. This is like the model getting closer and closer to the training data.
So the collapse time is like the moment when that ball gets stuck in a valley.
Precisely.
Unable to escape.
It's become trapped by a specific data point. Lost its ability to explore and generalize.
Right.
And this is where the random energy model comes in. It predicts that as energy decreases in a system, there's a phase transition where the system gets stuck in these low energy states.
So the model gets so fixated on a few specific data points that it loses sight of the big picture.
You got it. And this connection to the random energy model provides a mathematical framework for understanding why this collapse happens and how to potentially prevent it.
This is blowing my mind. We're using physics to understand the inner workings of a machine learning model.
It just goes to show that there are these profound connections between seemingly disparate fields.
And when we can bridge those gaps, we can unlock incredible insights.
This paper is a perfect example of that. But I'm feeling like I need a moment to process all of this. My brain is doing backflips over here.
I hear you. It's a lot to take in. But the good news is we're just getting started. There's one more fascinating connection to explore. The link between collapse in diffusion models and the concept of a glass transition in physics.
A glass transition?
Yes.
Now you're really piquing my curiosity. I have a vague recollection of that from my physics classes, but refresh my memory. What exactly is a glass transition?
So back to this glass transition thing. I remember it having something to do with liquids turning into solids, but I'm a bit fuzzy on the details. How does that relate to our diffusion model?
Well, think of it this way. When you cool down a liquid, like honey, the molecules start moving slower and slower, right? Eventually, they get so packed together they can barely move at all.
The honey becomes a glass.
I'm with you so far. But where do diffusion models come into the picture?
Think of the noise in our model as being like the temperature of the honey. At the start, lots of noise means things are hot. The model's bouncing around the data landscape, exploring freely. But as we remove noise, it's like we're cooling things down. The model's movements become more restricted.
So high noise is like a hot flowing liquid.
Yes.
Low noise is like that solidified glass.
Exactly.
I can see where this is going.
And just like with honey, if we cool things down too quickly, if we remove noise too abruptly, our model can get stuck in a particular configuration.
So that's our collapse time?
That's it. That's the collapse time.
The model becomes a glass fixed on specific data points, unable to generalize.
Exactly.
So the glass transition in physics is like a metaphor for what can happen to our diffusion model if we're not careful.
With the noise reduction process.
That's a pretty cool connection.
It is a cool connection,
And it gets even more interesting when we consider what physicists have learned about glass transitions. They found that as a liquid approaches that transition point, the arrangement of molecules becomes increasingly complex and disordered.
So it's like the data landscape becomes more rugged, harder to navigate.
That's a great way to put it. And for our diffusion model, this means that as it gets closer to collapse time, the relationship between the input data and its output gets incredibly tangled and complicated.
Which makes it even more likely the model will get trapped. Just like those honey molecules freezing in a disordered state.
Exactly. So this insight from physics gives us another way to think about overfitting, and it highlights how crucial it is to carefully manage that noise reduction process.
Like we need to cool the honey down slowly, giving those molecules time to settle into a more stable, ordered arrangement. Same with our model. We need to give it enough time to learn the underlying structure of the data. Without getting frozen in a messy, overfitted state.
Precisely. And this is where understanding speciation time and collapse time becomes so valuable. It's like having a thermometer to monitor the cooling process.
Because if we know when those transitions are likely to occur, we can adjust our noise reduction schedule accordingly.
Right.
Keeping the model in that sweet spot.
Yeah.
Between too much noise and too little.
Like Goldilocks finding the perfect temperature for her porridge.
Exactly.
That's it.
This entire deep dive has been incredible.
Okay.
I feel like we've not only uncovered some really useful tips for working with diffusion models, but we've also stumbled upon some mind-blowing connections between physics, machine learning, and finance.
It really highlights how important it is to be open to ideas from different fields.
Right.
Sometimes the solution to a problem in one area can be found in a completely unexpected place.
I couldn't agree more, and I think that's a great note to leave our listener with.
Before we wrap up completely, though, I do want to emphasize one point. For anyone using these models, especially in a field like computational finance, where the stakes can be high, remember that these are tools, powerful tools, but still just tools.
Meaning we can't just blindly rely on them.
Exactly.
Without careful thought and oversight.
It's up to us to use them responsibly and ethically, always keeping in mind the potential consequences, both positive and negative.
Well said. I think this deep dive has given us a lot to ponder, not just about the technical aspects of diffusion models, but also about their broader implications for the future of finance and beyond.
It's been a fascinating journey, and I'm excited to see where this field takes us next.
Me too. And to our listener, thank you for joining us on the deep dive. We hope you found this exploration of diffusion models as thought-provoking and inspiring as we have. Until next time, keep learning, keep questioning, and keep diving deep.